Anyway,
Anyways,
welcome to Theta Wave Podcast. Uh, my name is Ryan Reed. I am one of your hosts. I am a machine learning engineer, as well as a neuroscience researcher, um, and a um, songwriter, musician. Uh, and I'm here with my co-host, Jacob Holland.
hey guys.
Jacob is also a neuroscience researcher and is an actor as well as a musician. Jacob, what do we got going on today?
Alrighty, so we've got a couple things that I think we're gonna hit on today. So the first thing we're gonna talk about are LSTM autoencoders, which
Mm.
is very fascinating. I'll leave the details to you, but it's about compressing sequential data and then taking
So proud
that
of you.
and then after you compress the data, the decoder decodes that compressed data and tries to create the original input.
Wow.
So yeah, I remember last time you talked to me about it. And then uh along the same lines, I think we're gonna talk about the vanishing gradient problem. How as you back propagate the the gradient starts to vanish. And so if you don't know what that means, like I don't really know what that means, he's gonna explain it. And then I think we're gonna touch on a little bit of the AI fear mongering that's been going on
Mm-hmm.
in today's culture. Maybe touch on maybe where they have some right to be a little worried, but all of the big fuss might not be as troubling as one might think. So, alrighty, Ryan, let's hit off with some LSTM autoencoders.
Yeah.
All right, so what's that all about?
Well, you kind of explained it pretty well there.
Yes. All right.
The LS an LSTM autoencoder, and those for those that are more curious about LSTMs, we have a past video in which we went over some of the functionality of the LSTM cells, specifically the gates, and more specifically the forget gate. Um, but
Mm,
go back and check out that video if you're more curious about
yeah.
how LSTMs handle sequential data.
And that's the one with all the cool
Um,
visuals, right?
Yes, we actually have
Yes.
some nice visuals there in which animations that demonstrate kind of a lot of the processes that are
Yeah.
involved. And we tried to leave nothing abstract there,
Yeah.
so that you have a kind of complete representation of what's going on.
Hmm.
But we're kind of taking a little bit more of a high level approach here,
Yeah. Hmm.
with these LSTM autoencoders, and we've also gone over in the past autoencoders. I believe
Yes.
we had a video
Yeah, that was a while ago.
on a basic autoencoder,
Hmm.
which uses a dense basically dense fully interconnected layers in order
Mm,
to achieve something similar.
yeah.
But typically they're not designed for sequential data. And
Okay.
so,
This is more specific to
yes,
sequential
this is
data.
more specific to sequential data.
Mm,
And where this really shines, there have been a lot of attempts to, and a lot of methods created to handle the whole element of, as sequential data length increases,
mm.
it gets harder and harder to process that efficiently,
And why is that?
just because of the amount of data that's
The
going
amount
through
of
it. And
data.
so,
Okay.
you have attention mechanisms which were designed for this, so that you can pull out specific information from a larger context in a way that is important and relevant
Okay.
to your downstream processing.
Yeah.
And the problem with attention mechanisms, though, is that their computational size um, increases quadratically with the size of the input.
Mm.
And so,
Okay.
for really long sequences, such as maybe a 24-hour period of sample data, it's like that would be a massive, massive attention layer. And
so much detail,
unfeasible, like for like modern hardware. And so there have been other, attempts at coming up with solutions for this kind of problem. One of them is an LSTM autoencoder, and it bears a similar design to normal autoencoders, where if you imagine a pyramid, that's kind of the classic design for this autoencoder, where you have a large layer, like say like this size, followed by a slightly smaller layer, which is often designed in like half, like it'll half the increment.
Yeah.
And then a smaller layer, and then a smaller layer maybe. And you basically design these decreasing layers, and that will be the encoder. Okay. And then you have the mirrored version of that, the reverse, for the decoder. And so the purpose of this classic design is to try and by design force it to learn a more compressed representation of the data.
So it's taking the raw stuff and finding the most relevant values within it that can establish that a representation of that raw data.
Yes.
Pretty much.
So imagine like, and this will kind of give you, in essence, what it's trying to do there. Imagine you were looking at a 24-hour stock price history. You're looking at a 24-hour window, and you had like you could zoom in on the graph and like see it in more detail and whatnot, and you could zoom out, but your goal was you wanted to find a way to describe that to somebody and have it be as accurate a conveyal as possible, right?
Yeah.
What might be some of the things that you would look for or include? Like, let's say, in general, the graph's price follows this trend.
Okay.
Right? So from your perspective, that would be.
Yeah.
Okay. What would be some ways that you would try and describe that picture?
I would describe it as, all right, you can see that there is an initial high jump, then it curves down a little bit, and then goes up again a little bit more, even more, and then it slightly falls again.
So you might choose to pick out the peak points.
Yes.
And the valley points in that. You also might choose maybe some form of skew where like you choose where the majority of the values, i.e. the data, kind of where the majority of it, on what side it's on.
If it's more down, if it's more up.
Right.
Yeah.
And these are all things that you can use that will help reconstruct the important features of that data. But by forcing it to take this full representation and bring it down in size, you're never going to get a completely accurate reconstruction, right?
You can get close.
But that's kind of, we sign up for that whenever we're compressing something. Is that data loss there. But our goal is that we want to find the most important features that describe that data.
Okay.
And we do that by measuring it against the original input. So by adding the encoder, which forces it to lose features, and then the decoder, which forces it to reconstruct the whole thing, we are able to just compare it, the input versus, and have the output that is compared against be the original input. And so,
Interesting.
yeah, so we basically see what the encoder or the encoder and decoder output, and then compare how far that is from the original input.
And then from there, I guess you would then reconfigure the parameters or hyperparameters for retraining if it's like really bad.
So, the way that I recently did this, and went through a lot of different iterations of this architecture, in an attempt to get it to handle long-term data as well, appropriately, and also in an attempt to try and maximize its reconstruction detail.
Okay. How does that process work?
And well, we can probably get to that.
Okay.
I'm wondering if this is going to be too complex, but
give it your best shot. We've got some smart listeners.
So, well, I think we're assuming that our like 17 listeners are. I'm assuming if they like it, that they are capable of understanding it. So that's probably a valid assumption.
Yeah, try to give like maybe like a simple.
Okay, so when we keep in mind, I was not prepared for this part of explaining, so I'm gonna have to work through it as I go.
I'm so curious.
When we put in data into a machine learning model, one of the common practices is something called scaling.
Okay.
And it's when we translate our data from the original values to a range between 0 and 1.
Okay.
Sorry. Yeah, no, that is right. It's between 0 and 1. And the purpose for this is there's multiple purposes for this. One of which is that our current model architectures revolve around something called floating point numbers, which are basically decimal point numbers that have a certain precision, so a certain amount of decimal points, basically, that that they can extend to, and for example, 64-bit precision has a much more detailed picture of a decimal point place than a 32-point or a 32-bit precision. So, I mean, again, this is getting kind of technical, but like we scale it, and it's not just for that. We also do it to avoid something called the exploding gradient problem, which is not something that we're gonna really go over today. But it's basically a result of your numbers being too large that you're inputting into the model.
I see. As opposed to being too small.
Right.
Yeah.
Which
is the other problem.
Is the reverse of the exploding gradient, which is the vanishing gradient.
I see.
And so we scale our data to keep it within a kind of a definable, predictable range that works with the architectures. And what was the original question?
Oh God,
I lost track of the original question.
We were talking about it was the process of we were talking about the autoencoders, and that led to you. I think we were talking about how it's utilized, something along those lines. Then I was like, wait, how do you actually do that? We can just floating point numbers. Why were we? Because there was like something right before that. I'm talking about floating point numbers, gradient problem. It was something.
Or just listen back to our podcast.
Long-term data. Oh,
Oh
maximizing
yes,
its
okay. That's
reconstruction.
that's where we're at. Okay.
Yeah.
Sorry about that. So when we are comparing, typically one of the most basic things that you look at is the loss function, such as the mean squared error, and the mean or the mean absolute error. Like these are loss metrics that describe how far off a output is from an input, and how well the model is doing. And so that's the most basic form that we take a look at, and our goal is in those cases, this case, to minimize that loss.
Yeah.
However, those aren't exactly intuitive for us to understand how well they give us a metric by which to gauge performance, comparative performance, on previous runs, but they don't really tell us how, in and of themselves, don't really tell us how close our data is to what it should be. Like, for instance, if I have a loss of 0.0001, that could be good or that could be bad, depending on the range of values that I'm dealing with and the average value there.
Okay.
And so one of the metrics that we can do is basically this is the reason I told you about the scaling, because that metric, that 0001, is calculated off of our scaled data, our scaled version of it, not the meaningful version for us, not the original value. So let's say the original stock price that we were tracking was, $25,000. In a decimal point format, that might look like a whole lot of different things depending on the scale that we're dealing with.
I see.
And so what we have to do is basically calculate some extra metrics on top of it. Like, for instance, we can calculate the difference between the two, but before we do that, we have to rescale it. We have to turn it back, the data back into its original scale, so that we can view it within the range that is meaningful to us.
Oh, I see.
So we turn it back into its original scale. Then we calculate the difference maybe between them, or the average difference between them, and we can even calculate the percentage, the difference between them relative to the average. So essentially saying this is only 1% off from the average value, and those can all give us an idea of, in general, how well our reconstruction is describing, how well the encoder and decoder are reconstructing the data.
Okay. Okay. So those additional metrics that relate to the original.
Those original metrics are not for training purposes. They're for us evaluating
Hmm.
how well the model is actually doing so that we can decide when we need to stop training,
Yeah. Okay. I see.
and what needs to be done and what further improvements need to be made.
Mm-hmm.
So that's kind of all involved in the evaluation phase. Another interesting concept, well, at least I find it interesting in machine learning, that most people wouldn't be aware of is the fact that with every model that we train, we have a training data set. We have an overarching data set that's split into training and validation data sets. Training is the majority of that split there. The majority of the data is used for training. We train the model on it, but we have a small portion of it that we reserve for validation that the model never sees. We never use it for training
Mm-hmm.
because it is important that the model never see that information, because it tells us how well our model is actually doing. Like, because it's unseen data, meaning that it's more accurately reflects real world scenarios,
Mm.
and tells us if our model is just overfitting, which is when it learns a data set so thoroughly that it can like really accurately predict things within that data set,
But just that.
but just that.
Mm-hmm.
And that's something we want to avoid. And so it tells us if our model is overfitting, if it's capable of handling situations that it's not seen, which will let us know if it's accurately picking up on the essence of and fundamentals of
Mm-hmm.
the task that is being
Okay.
required to do. And so the typically a lot of those metrics are calculated on the validation data,
Mm-hmm.
to avoid the possibility of of getting kind of a skewed perspective on how well your model is doing.
Yeah.
And so that's kind of a side detour there,
Mm-hmm. A little bit.
and kind of some interesting components that are extend beyond just LSTM autoencoders.
I see.
But
There's still fundamental to it, though, right?
I mean, yes, because
process
they're
of
this
training.
fundamental to the training process.
I see.
For deep learning. But during this process, I wanted to improve the accuracy, and I have something. A lot of these models are because of the fact that there is multiple LSTMs involved, as well as partly as a result of the way that I set up my training data. But there's potentially susceptible to overfitting, but there's a very key balance with these LSTM autoencoders that is determined primarily by the junction size of where the encoder meets the decoder.
Okay.
So that
I
size
see.
there determines, because you like think about it, like you're essentially telling it its limits there of like you have this many data points to describe this period of data.
Mm.
And so if you make it too large, it can just learn to represent the training data too well.
Yeah.
Within that frame.
It's like instead of giving it a pyramid, you're giving it like a block.
Yeah, yeah.
A square or something.
Or like instead of like forcing it to learn compression, you're forcing it to learn like a description of your data, and
Mm.
and yes, you want a description, but you want a compressed description.
Yeah, exactly.
And so, if you make that size too big, it starts overfitting and learns just patterns within your training data.
Mm.
And that's what it puts in so that's not what we want. We want feature extraction. And so, but if you make it too small, then it's not going to be able to accurately reconstruct
I see. Yeah.
the information.
Just want to make sure that it's in that kind of Goldilocks zone.
Exactly. Yes. And so, that junction size is something that I had to play around a lot with to figure out what happens when I change that size.
Mm-hmm.
And one interesting thing that I found there is that surprisingly, the junction size that handles a 6-hour period of time or a 3-hour period of time also works for a 12-hour period of time.
Oh, interesting.
I know.
Huh.
You would think that junction size would need to increase, as your period of time increase, because there's more
data to work with.
But it works pretty much just as well for the 12-hour period.
I remember you telling me about that. Do you remember your explanation as to, or like why you think it was able to have the same good scores with bigger data sets?
Well, and I will say this, initially there was a little bit of an error in my logic which I hate to admit, but like there was an error in my logic of the model training in which I was not, and I really just wasn't thinking this through, but like I was randomizing my data sets and then splitting it, and then splitting the data. So the model was actually getting to see the validation data.
Oh,
there was a leak in my data into the validation. And so that was giving me an unrealistic perspective of my model's performance. Once I realized that, I fixed it, saw how my model was actually performing, and then had to make some further tuning and adjustments in order to resolve that. So now it is back to
that.
Not exactly where it was, but it's still doing really well. And I see that same trend play out that I had happened before, where it's
still consistent limits across the time frames,
right? And which basically just implies that the model implies like one or two things, or both. A, that the model is learning the most essential features to data across all time frames to describing it. Or B, that the most important features in a overarching big picture view are contained within a smaller period of time, like a 3-hour window or a 1-hour window.
I see. Yeah.
And so either way, it's able to handle that reconstruction, which is nice.
That's very good.
But there was a change that I made in order to try and get the model scores back to where I wanted them after I realized the validation leak that was happening. And that was to make the model's width larger. So I added 3 LSTM layers for the encoder and 3 for the decoder.
Yeah.
And this brings up a really important concept in development in modern deep learning architectures that involve very, very the depth.
So
the depth of the model.
And is that like the density of the layering as opposed to like the size of the neuron
It
layers?
has to do with like how many layers are in a row.
Okay.
So when the data passes through,
Mm-hmm.
how many different components is it having to
Yeah.
pass through, in calculations. Um, and so as the model's depth increases, that's a deeper, you know, uh, that's a deeper model, and larger models like Gemini and Llama, um, blanking right now. I'm blank for why.
Claude?
Claude. Thank you.
Yeah.
Those models typically they're massively deep
Oh
models.
my goodness, yeah.
Now
So computationally expensive.
I
Insane.
ran into, and I didn't realize I was going to really run into it at this depth, because it's not, as far as possible, like model depths, like it's definitely still a deeper model, but
Yeah.
it's not anywhere near some of the other ones. I didn't really realize I was going to run into this until I ran into it. But adding those extra layers caused an issue where, and I noticed this through my graphs, right? My There's some visual metrics that we keep track of, and one of those automatically for all models that I train is both the gradients and the weights of the different layers to watch how those are changing, um and I noticed first off that my loss didn't seem to be improving, which I found surprising for a 3 layer. For the extra layers, you'd think that the loss would improve. There were a couple different explanations for that, but once I took a look at my gradients and my weight graphs, I realized that the earlier layers in my model barely had any weights, then they were not being adjusted very much at all.
Oh, I see.
And I was like, oh, that makes sense why I'm not getting an improvement in my loss function, because I was running into the vanishing gradient problem,
Let's dive
which
a little bit deeper into that.
which happens as a model's depth increases. And basically, I don't want to dive fully into the vanishing gradient problem because it involves a lot of really hard concepts that I want to kind of devote their own period of time to and really diving into, but I will go over it from a kind of basic level so that it can be understood.
Okay.
But the vanishing gradient problem happens during a phase called backpropagation within machine learning training process.
That's when it's going back through the layers.
Which is basically when it's sending like signal back through the layers and like adjusting weights and trying to determine. It's this backpropagation is built off of a calculus concept called the chain rule.
Oh yeah. Right.
And basically is trying to determine how important a weight is to an output, right? So in order to figure out how much it needs to be tuned and adjusted. Now, unfortunately, that inherently means that weights that are closer to the output are going to appear to have a higher value and impact, and thus are going to be subject to the most change, and the ones that are further away from the output are going to look like they are less.
Yeah.
And
I see.
this, you can imagine this kind of like a game of telephone, where each successive person can only say a fraction of the word count that was used by the person that told them.
I see.
So, like, let's say I tell you that I want you to go to the store and pick up 3 gallons of milk, or I want someone to go to the store and pick up 3 gallons of milk, a gallon or a container of orange juice, 3 cartons of eggs. Like, I'm giving all these details and like using a specific amount of words, and then you need to go convey that to another person, but you're limited to 80% of the words that I use. So you got to cut out some information there, and then that person tells the person that's actually going to go to the store, but they're limited to 40%. And so information, and thus like the signal is getting quieter and quieter, the or less and less distinct, the more it travels through this and it has to do with the algorithm used for back propagation and the chain rule and whatnot, but which we're not going to dive into now. But that's basically what's happening, is that things further away are appearing to have less of an impact on the outputs because of that loss of information that's happening.
That's because is that because you're multiplying the partial derivatives per layer, so you get like an increase exponentially? So like a value that goes into it would be like a 0.1 value to the power of 10th is like 10 layers, and the power of 20th 20 layers. So it's like increased to like 1,000 times the original, and then to like 1,000,000. And then at that point, once you get past that point, there's really no differential distinction between the value points in the gradient. Is that
kind of? Yeah. That's in essence, it's what the, especially the first part of what you said, like is true. And again, like, I don't want to delve too much into the math because that's going to add too many technical details that are not optimal for this situation. Like, there should be visuals to visualize this stuff.
Okay, yeah, it'd be a little more intuitive.
But that is basically what's happening, and so there are methods that we have come up with to combat this, that are inherent to modern day deep learning architecture, and have to be used in order to enable that to even happen.
Okay.
With like all those layers, because otherwise you will get early layers that don't learn anything. And so one of these methods that I had to employ in order to fix this problem was first off a projection layer, which is basically a layer that is built for the purpose only of changing the shape of the data at a specific point.
Okay.
So like, as a model increases, the shape is going to increase, right? Like, of the data, because it's going to be outputting more. It's going to be outputting more data as the layers increase in size, and then as they decrease in size, it's going to be outputting less data, so that shape is going to decrease.
I see.
And so there is a method that is used to combat this vanishing gradient problem, where you add the input from one layer to its output, and so you basically are maintaining signal strength by adding the original input back to the output, and so you're getting changes from inputs to outputs, but you're not reducing the data.
Okay.
So it's basically like, almost like, think of it like, those points on axons that work to amplify a signal as it's traveling down the axon.
Myelin sheets.
Yes, and they are able to maintain the signal strength through really long axons.
Yeah.
Through these amplification steps, right?
Mm-hmm. Yeah, there's no loss.
Right. That's kind of what's happening here. Is
okay.
We are feeding the original signal back into it to amplify it as it's traveling through this network.
So instead of there being kind of this game of telephone, it's almost like this game of catch.
Right. It's almost like you reiterate everything that they said, and you bring out the important points again.
Mm-hmm.
And so, like, you're still doing some distillation, but you're not losing information in the process.
Mm-hmm.
And so, it's kind of just, the goal is to like maintain that signal strength so that it can travel all the way through, the network. And in combination with that, we use what's called a normalization layer, which...
Is that like normalizing audio?
Yeah, kind of.
Okay.
It's basically to control some of the potentially negative outcomes of amplifying, the signal.
I see.
And to kind of make everything, contain everything, within a range. So those two are both necessary and complementary to each other, the adding of the signal and then the normalization of the signal. And they do reflect like a lot of those same processes that the cells and axons go through in the human brain. But that has to happen after, like, pretty much, usually it happens after like every layer as you get through to those deeper and deeper networks, because you have to maintain that signal strength.
Okay, I see.
That's cool. And so that was something that I had to implement into this LSTM autoencoder because the depth had increased. The previous version was able to handle it because it wasn't very deep. There was just 2 layers in the encoder and 2 layers in the outcoder.
Yeah,
or in the encoder, in the encoder, and then 2 layers in the decoder. And but the 3-layer point, it started having this kind of like this diminishing return problem, and so that basically to kind of connect it all together, the input, if you remember matrix multiplication, right?
Yeah.
You had the one size that was determined by the input, that one size of neurons that's determined by the input, but being a fully connected layer, like the you also have that output. So how is it being output? And with these, the output has to be determined by the layer that it's gonna connect to.
Mm-hmm.
And so because of the way that these LSTMs are designed, that hidden size that determines its output size has to be the same size as the next one that it's connecting to. So that means the input and the output to an LSTM in these autoencoders is going to be different, which means I can't just add them together because there's not the same amount of elements there. So you can't just add element wise, and so, and again, just remember element wise is per item. Like you can't if you have a tensor of like 10 items and a tensor of 10 items, you can add each item individually together.
Yeah.
But if you have a tensor of 5 items and a tensor of 10 items, how do you add those together? You can't. And so it's important they are the same shape. And so that is where that projection layer comes in.
Interesting.
You input you have a layer specifically designed to take the original input, transform it and reshape it into a the same size as the output, so that you can add it to the output and maintain the signal strength.
Oh, interesting. Seems like a very clever way to fix that problem.
Yeah.
I will say. And to me, I guess it might seem at first it's like the projection layer would almost seem at first glance arbitrary in a sense, just to like match it, just like add kind of like, it's like kind of picking the person on your on your team that you don't really want, but the last person there to kind of fill
you need
void
in order to fill out the team.
Yeah. But do they have some sort of like value in essence besides that addition to kind of make it the same, even out the playing field?
Projection layers are there to make things the right shape. The value that they add is letting you do that process of signal amplification. And so they take that input and transform it in a way that can be amplified. They can amplify the output. That is their job.
Okay. Yeah, that definitely. So it's kind of like the myelin sheath. It's not like actually getting the signal. It's just that amplification to maintain signal strength.
Yeah,
I see.
It's like if the I'm not sure if this actually is the case, but if the axon had a way to convert a signal and split it so that it could amplify at each individual point along its axon. So like if it could take a signal coming from somewhere else and then it could split it off and use it to amplify like these, points along this axon. That's like what it's doing. It's transforming it into the necessary number of amplification steps.
Okay. Yeah, that definitely makes sense.
Interesting. Yeah, and it's just kind of one of those like weird nuances that you don't run into unless you're creating a deeper architecture. And it then becomes very necessary to implement.
Oh yeah, absolutely.
And so yeah, I mean that's the kind of in essence how you would build an LSTM autoencoder. On this very base level, it's just a sequence of LSTMs that learn to encode and decode.
And the LSTMs are like the forget gates. What are the other? You
have the in gate. Yes.
In gate. Yeah.
The in gate, forget gate, and the out gate.
Okay. Yeah. Those three. Yeah.
And then you have like a cell that in the combination phase that adds those components to long-term memory.
Okay, so it goes through that process.
So you have your hidden state, which and then your cell state. Your cell state being the long-term memory, your hidden state being the short-term memory. That gets passed, as the as you feed data through it,
And then as you feed the data through it, and then you get the output, is that when the autoencoder process happens? After or during?
the autoencoder process happens all the time.
All the time.
Like
Okay, so
it's
while it's running. I see.
right. So as
Mhm.
data is passing from one LSTM to the next, like
Ah, okay.
each
Yeah.
like each output gets passed to the next LSTM, which then processes it, which gets passed to the next LSTM, which processes it.
Oh, that's interesting. So pretty much what you're saying is that it's almost like a link between the LSTMs to where you're having their and process the data in the LSTM, and that gets put through this encode decode process to get to the next one and does this over and over again.
Mm-hmm.
And I guess the implications of kind of looping that, where you have that LSTM to encode to decode to do that, does that give you a very finely tuned value system to work with at the end of result of that training
What
when
do you
you like
mean?
do it over and over and over again through all these LSTMs?
What do you mean?
Like when you do like this when you like compress the data and then give it to the next LSTM, and then it compresses the data and give it to the next LSTM.
Mm-hmm.
That does that give it just um more accuracy?
Yeah, well, it gives it greater ability to store and information over time, as well as the ability to focus on different features. Imagine if I were asking you, as an expert, to memorize the shape for a bunch of different sequential features, so like
Mm-hmm.
the open and closing price of something, or
Yeah.
in the volume, and I wanted you to be able to describe efficiently a 24-hour window of time of that shape for each of those features. That's going to be really hard for
Yeah,
you
it's
to
gonna be a
do
lot.
and keep things straight, like keep things,
Oh, absolutely.
you know but you allow three different people to work on those individually and choose figure out what things they're going to be in charge of focusing on. Maybe one person focuses on peaks,
Mm-hmm.
or maybe another person, or maybe he focuses on a specific feature,
Okay.
but you allow focus, and then stages. So he passes off what he's found
Mm-hmm.
to the next person, and then the
I
next
see.
person just advances that.
Okay.
And so um, that's going to be a whole lot more suited for long-term, like, sequence data
Yeah.
than just kind of having one do it, and specifically that designing that pyramidal structure um, encourages that desired compression to happen there.
Mm-hmm.
Um, and so there is an interesting element too, where um, you remember the hidden state and the cell state, long-term memory, hidden state,
Mm-hmm.
short-term memory. So at the point where the junctions meet between the encoder and the decoder, the last LSTM cell in the encoder passes its cell state and its hidden state to the first cell in the decoder. So essentially, its long-term memory and short-term memory become the first cell's long-term memory and short-term memory.
Okay.
That's how it essentially achieves that cohesion there,
Mm-hmm.
and and you pass through the entire sequence through the decoder again as a guiding principle for it to figure out what it's doing. But Yeah, it's that handoff between the encoder and the decoder there that's important.
Okay, yeah, that's
Because in a real world scenario, you don't feed the decoder the data again. You don't feed it that historical data. You actually feed it zeros.
ah,
You give it zeros and let its learned behavior via the cell and the hidden states
mm-hmm.
fill that information out.
Fill it out. Okay, interesting. All right.
So when we're okay, and to better explain that, because I realized I skipped over a step there.
Oh.
You're not using the decoder there because the decoder gets thrown away. You're
Yeah.
using what is put in place of the decoder, which is another LSTM cell.
Oh.
You're using another LSTM cell to make predictions based off of that encoded information.
Mm-hmm.
So what you are doing is you're passing that hidden state and the cell state to the new LSTM cell that's going to be trained to make predictions, and you feed that LSTM cell zeros.
Okay.
Obviously, because it's like predicting future, not.
Mm-hmm. Oh, I see. Yeah. But it's still, is it predicting based off of what the encoder is giving it?
Yes. So the encoder, it passes its hidden in cell state as gathered information. Like, you remember, those represent the features that it has stored in its memory from the data that is passed through it. So by training that, we were trying to compress the data into the important bits.
Yeah.
That cell state and the hidden state represent those important bits.
Mm.
So we pass it almost like transferring memory into this next LSTM cell, so that it has that knowledge that is needed.
Yeah, that actually ties this whole concept together really well and kind of puts that encoder aspect to it into a functional mechanism, because at first glance you're like, okay, it's cool that it's able to compress into a value and then it's able to represent it. What is it actually?
But what is the purpose of that? Yeah,
it's for that training process to where you know that it's accurately representing the most vital values that you need to give to the eventual LSTM cell.
Exactly.
To make predictions.
Exactly. The like previously for me, what I was acting as that part. Like, I was playing that encoder part where I was trying to determine how best to format the data and compress it down into these windows that represented things well enough for it to make predictions off of. That's not very efficient because I don't have the communication ability with the model that a integrated part of the model would.
Yeah.
And so by automating this process of feature extraction there from those longer windows, and then, like I was saying, through that transfer that happens there, you no longer have to worry about getting that right.
Yeah.
Because the model's been trained to do it. And so transfer that over to the next LSTM. That LSTM gets trained to use that information in order to make projective, like, calculations. So, like, what it thinks based on that is going to happen next.
Yeah. Okay. Oh, that is so cool. That's a really cool concept.
It is.
I have to let that marinate in my brain. Fascinating.
It's just another one of those, like, crazy, like, man, that is just, like, so complex, but, like, also
so beautifully
really
logical.
Yeah.
Yeah. It's like, when you were to look at it from a higher level view, you're like, oh, well, obviously this is how it works and this makes sense. But then when you get into the details, you can understand the more profound implications.
Like the why and how.
Yeah, the how is really huge. You know, how it all kind of ties together.
Yeah.
A little bit. Yeah, it's very interesting. All right.
If you
So,
can't tell, I have a kind of, and I don't know where this exactly came from, but I have a special affinity for
mm,
LSTMs in general. Like, and I've noticed that, like that for whatever reason, my, I mean, there are other architectures that I find interesting. You know, reinforcement learning is another one that I'm really passionate about. But like, for whatever reason, LSTMs have like really grabbed my attention. Most people, I'd say that's not really common. Most people are interested in diffusers, transformers,
yeah.
like um, the attention mechanisms that are like enable a lot of the modern large language models. And to me, I've never found that to be particularly interesting. Like, I mean, they're
Cool.
useful and
Yeah.
it's cool, but they have some severe problems and that limit their usability. Like, for
Yeah.
instance, I was saying with the attention mechanisms, like they make really, really like heavy duty models that are hard to run on a lot of hardware. And then take that in comparison with an LSTM that is just so beautifully small and fast.
Yeah.
Like,
It's just different.
yeah, you know, it might take it a bit to process a sequence because it doesn't do it in parallel
Yeah.
um, like a attention mechanism does. And for those that don't know, parallel means is when all computations are being processed at one time,
Yeah.
and it does it sequentially, more like a CPU, where it takes each step and like
I see.
but it is a very lightweight and very fast at what it does.
Mm-hmm.
For the most part. Like, we should have seen some of the encoders that I was training. Like, they were just like speeding through my
Zipping.
data.
It's beautiful.
And I was feeding it a lot. Like, I was feeding it a year's worth of minute data.
Dang. That's a
Not
lot.
only, okay, now I want you to take this in full context. Not only was I feeding it a year's worth of minute data, I was feeding it a year's worth of 24-hour sliding windows, meaning I was taking a 24-hour window, so 60 minutes times 24. Then I would slide it by one and copy that data, slide it by one, copy that data. So you actually have repeated data, which makes that so much longer, because you are essentially multiplying it by the same length as the window.
Mm-hmm.
And so 60 times 24 times however many minutes are in a year.
Yeah. I forget
That,
the number.
anyway, so that's what you're feeding this thing. And so it's the fact that it's able to zip through it that fast is just, phenomenal.
Oh yeah. Absolutely. All right.
All right.
So
Well, I think we're going to take a coffee break.
a little bit of a break.
Yep. And we will be back to discuss some of the possible worries, concerns,
Mm-hmm.
and more specifically, societal attitudes that have been propagated towards AI recently.
It it is 2:20. Very late. Would you perhaps want to save that for Tuesday for our free flow?
Sure. I mean, if we need to.
Yeah, that would be nice. Just so I can get a good amount of sleep.
Okay.
Yeah.
Sure. Yeah. Do what you gotta do.
Okay,
All right. Well, then we'll be covering that topic
Tuesday.
on Tuesday.
After we have a really fun conversation about the dopaminergic complex. Yeah, which is going to be so cool.
Excited about that one.
Absolutely. This definitely was an interesting conversation. I had to hold my tongue a little bit to not make like neuroscience analogies or references to it. I was like, I'll take us down the wrong path. Can't do it.
Nothing wrong with that. Some people might be a little more familiar with some of those concepts. You know?
Yeah, like with the myelin sheath. That one made a lot of sense to me. But anyways, thank you guys so much for tuning in. Really appreciate you guys. And yeah, catch you next time for another fascinating conversation here on Theta Wave. All right.
See you guys.
See ya.